Okay, so I'll start. So my topic today is we have done some calculations, conductivity calculations from first principles on high entropy alloys, and I'm going to discuss what we did and what results we got and how we analyzed those results. So here's the agenda for today's talk. I'm going to give a brief introduction to high entropy alloys. Then I'm going to again talk about the KKR-CPA method and specifically how you can calculate conductivity within the KKR-CPA formalism using the Kubo-Greenwood formula. And then we've implemented that in the must code. So first I'm going to show some examples that have already been done. So copper, zinc, and silver, palladium have been, these conductivity calculations have been done for several years now. And they act as a good unit test. And then as an intermediate test, I'm going to show the application of our code on the Cantervue alloys, which was, there was a paper by Sai Mu on where these alloys were studied. So again, this serves as a sort of comparison to show that our code is functional. Then we're going to apply it to the multi-phase high entropy alloy system, which is aluminum, cobalt, chromium, iron, nickel. Now at low aluminum concentrations, this is BCC, and this is FCC, and at high aluminum concentrations, this is BCC. But at intermediate concentrations, it's a mixed FCC plus BCC phase. So that has some interesting effects on the conductivity. And we're going to compare that to experiment. And then finally, we're going to give a prediction for the refractory high entropy alloy, molybdenum, niobium, tantalum, vanadium, tungsten, as a function of the vanadium concentration. And yeah, so that's basically it. So high entropy alloys, there are multiple ways to define this, but generally it is understood that alloys with 4 or 5 principal elements, these elements are generally transition metals, and they're equiatomic or nearly equiatomic, and that is their concentrations varies from 5 to 35%. They're also referred to as compositionally complex alloys, and this is a sort of counterintuitive idea when it was initially proposed, because people thought if you put more elements in an alloy, you're increasing the chance that there will be some intermetallic compounds forming, and you won't see a single phase. But actually, because of the high chemical disorder, the free energy is stabilized by the entropy. So in these systems, you will see there is a high chance of seeing a single phase solid solution being stabilized as opposed to other intermetallic compounds that may be formed. The reason high entropy alloys are exciting and people study it a lot is they have really useful and interesting functional properties. So for example, one of the first high entropy alloys is the Cantervue alloy, which is cobalt, chromium, iron, manganese, nickel. It has very good mechanical properties, high ultimate strengths, large elongations. And for example, this copper, cobalt, iron, manganese, nickel is a substrate for graphene growth. This high entropy alloy.
Question, Vishnu. I
Yeah.
have a question. What can you just when you use these words like elongation? Some of us are not. I'm not familiar with what exactly that means. Can you refresh or tell us exactly what this is? Elongations.
So elongation is, I think, essentially it's a measure of ductility. So you're stretching a material, and you're seeing at which point it breaks.
I see, but this is beyond the elastic regime, right? This it's a plastic deformation, is it?
Yeah.
Yes.
Yeah, there is. So you would expect at some point you would go to some sort of instability.
But my question is, does it, when you stretch it like this just before the point of breaking, does it remain? So if you release it, does it remain elongated or it contracts back? Because I somehow remember that some of these high entropy alloys are actually very mechanically hard, and they actually have strong elastic properties as well. So I'm trying to distinguish the elastic and the plastic regime.
I think at small strains they will go back, but we expect that beyond at large strains, if you release it, it will not go back. It will be in the plastic region. In fact, for some, actually, we've been looking at BCC high entropy alloys. And for BCC high entropy alloys, if you start with a cubic structure and you stretch it, then beyond a point, it goes to a transition where it goes from cubic to some sort of orthorhombic face center structure. And that enables it to be ductile. That is what we found. So it varies from system to system, but beyond some strains, it does not remain in the elastic region. That is
right. That's very interesting. Thank you.
Just as a reference, but if I'm going to just say something as a reference point, one of the amazing things that was discovered early in this game is that some of these materials, so when metals, you cool down alloys to very low temperature, they become, in fact, they become stronger, but they become brittle.
Right.
And what happens in these, and when so many of these materials, and particularly one of the good examples is the 5-component equiatomic one of the 3D elements, that as they get colder, they certainly get stronger, but they also get more ductile. You can stretch these almost like an elastic band. Well, except the elastic band will go back, but this thing just default. Well, like toffee, right? Warm toffee.
I see. This is really interesting. I'm sorry to interrupt all the time, but this is I think a very central issue. So as opposed to, I've been told the metallic glasses, which are not periodic, which are not crystalline alloys, but are amorphous, they actually are brittle and they're not ductile like that, right? Is that correct?
Yeah. So you said they're brittle.
They are brittle. So this property is specific to these high entropy alloys and differentiates them from glassy metals. So is it clear why that happens? Why is it so ductile and not brittle?
In a metallic glass, a lot of the mechanisms by which metals distort, motion of dislocations, forming of twin boundaries, this kind of stuff. Those are not, they mostly don't happen or are forbidden in the metallic glass because of the lack of periodicity.
Here they do.
But here in these, this FCC alloy, all of these other, there are lots of mechanisms. It turns out there are lots of mechanisms that account for this. It's not just the pristine material. So what happens is you get different of these methods by which, these mechanisms by which metals distort happen. Some of them are just, some of them are even that you get a phase change. Right, so it would go from cubic to tetragonal or something like that as you distort it, right?
I see.
And
very nice.
It's this thing I think I mentioned once before. It's the hood of your car is made out of materials that absorb energy, right? Of metals that crumple,
right,
and soak up the energy. It's a very similar. Some of those mechanisms are relevant to these high entropy alloys at low temperature.
Right, because they are crystalline, that's what we expect. But then the fact that they're alloys, that actually brings a new dimension that's not in elemental metals, right?
Yeah, exactly.
Thank you.
So strong and ductile at cryogenic temperatures is something that people are very interested in.
Right. Awesome, thank you.
Also, some high entropy alloys, for example, this hafnium, niobium, tantalum, titanium, zirconium, has been shown to has demonstrated superconductivity. So basically, these high entropy alloys have the potential for great mechanical and electrical properties. So there's a lot of research going on trying to synthesize suitable alloys, trying to find in what concentrations you need to put which elements to get the desirable properties. There are some examples here of functional properties that are very useful that currently there's some research going on. So we're trying to do some conductivity calculations on these high entropy alloys, and we're using the CPA technique, which is essentially you're replacing your alloy, which consists of multiple elements, and it has various different configurations. You're replacing it with an effective medium, which behaves like your ensemble average. So essentially, you're dealing with a pure element single crystal, which computationally makes things very easy. Now, we are also in the single site approximation, which means we're not dealing with any correlations in the chemical species between the neighbors. The species distribution on each site is controlled purely by the global concentrations that you specify for the individual species. And the way you do that is through these equations here, where you create a single site impurity and you calculate the tau matrix, the multiple scattering path matrix associated with that, which is given by equation 2 here, and then you average it to get tau CPA. So you can essentially construct a self-consistent iteration scheme to get the T matrix and the tau matrix for the single site CPA medium. Now, obviously, the drawback of this is that you are missing out on short range order. And there are other methods right now, like the non-local CPA or the cluster average CPA, which can, or the embedded cluster method, which can take care of this can take care of short range order in the alloy. But for now, we're only in the single site regime. So when it comes to electrical resistivity, there are several techniques available. So you can solve the semi-classical Boltzmann transport equation to get but in this technique you need the bands, and if you have a highly random system, then there's a lot of smearing and your bands at the Fermi energy may not be well defined. So using the semi-classical Boltzmann transport equation may not be feasible for highly random alloys. So we are using the Kubo-Greenwood formula, which is the Kubo-Greenwood linear response. So the idea is basically you have some unperturbed Hamiltonian, and you're adding a small electric field, and you're considering that as a perturbation. And within this perturbative theory, you can express the conductivity as a current correlation operation given here in equation 3. And you can, in fact, even this over here is the expectation value with respect to the unperturbed Hamiltonian, which is why you have this 0 here in the subscript. And in the DC case, which is basically when you have omega equal to 0 and at t equal to 0, you can express the same equation 3 in terms of these wave functions here. And this is the Kubo-Greenwood expression. And here you have these large outer brackets. This is for a random system. So basically, in a random system can be expressed as an ensemble of different configurations. And you basically calculate this for each configuration, and you take an ensemble average, which is how you would go about doing this calculation for a random system. Now we are using the KKR method. In the KKR method, we don't deal with system wave functions. We only use single site wave functions and a system's Green's function. So we would like to convert this into some expression that has Green's functions, or rather that uses multiple scattering matrices, because that is what we have with us in this method. And basically with a lot of algebra, you can convert that into this form, where you express sigma in terms of these sigma tilde functions at 2 energy points, which is epsilon f plus I delta and epsilon f minus I delta, which is basically delta is a small imaginary part slightly above and slightly below the Fermi energy. And each sigma tilde term can be expressed as equation 7 here, using the current matrix, which is basically you have the current operator, but expressed as matrix elements in the position basis. and tau matrix, which is your multiple scattering path matrix, between any two sites M and N. And these angular brackets here are the ensemble average. So this is still the same Kubo-Greenwood expression, but now instead of dealing with wave functions, we are expressed it in the language of scattering theory, which is you have tau matrices. Now we still need to deal with this ensemble average, because we are now in the CPA regime now, and in CPA you don't really deal with configurations anymore. You deal with an effective medium. So you need to re-express this in terms of tau CPA matrix or CPA tau matrices. And again, that can be done with a lot of algebra, and you can convert sigma tilde into sigma tilde 0 plus sigma tilde 1. There is a paper by Butler from 1985, I think, which is basically has all the steps from how you go from that starting to this formula. And I can link that paper at the end of the talk if anyone's interested.
I just want to clarify something here. Here there's a sigma 1 with the vertex some vertex correction.
Yeah.
So I'm not particularly familiar with the KKR version, even though I know something about it, but it's more complicated because there are many bands and it's a continuum theory. Now, in the case of a single band model, I just would like to kind of clarify, if you apply the same procedure and you have a single band model, right? The same KKR-CPA can be done also for one or for any number of bands. The standard CPA is an approximation that becomes exact in the, I'm talking about one band model, in infinite dimensions. If you have a large coordination number, just like the DMFT, and then the vertex corrections happen to drop out. So can you actually comment on this? Are these vertex corrections, if we actually looked at the single band situation, would these vertex corrections drop out by symmetry? And is the self energy in the CPA, just like in the MFT, the self energy is purely local. In the KKR version, it will be local to the atom or to the itself.
Are you referring to this vertex correction term here?
Yes.
Yeah, actually that has really, I don't think, anything to do with the vertex corrections that you are referring to. I think this vertex corrections is specific only to this conductivity term, where it refers to the sort of scattering in. So I have a slide on this. So basically, so if you express like the Boltzmann equation version of this, so F is your distribution function, and with respect to energy, and you express it this way, then you have these two terms here. One is, say, scattering from Q to Q prime, and then scattering from Q prime to Q. So if you ignore the Q prime to Q term, which is the scattering in term, the back scattering, if you ignore the second term, that's what is referred to as ignoring vertex correction. So that doesn't have anything to do with the many body vertex correction.
When people have studied systematically weak disorder, effects of disorder on metals using perturbative methods. So then it's standard within Boltzmann-Trump sport or within the Kubo formula that there are ladder. One has to sum some ladder diagrams to calculate vertex correction and gives you the cosine theta term. But that's different from so-called maximal cross diagrams that give you weak localization, which is another vertex correction. And I'm just trying to understand, this is now in a language that's specific to this KKR implementation. But if we actually, I'm trying to see, to what extent, it's the CPA applied for a single band model. The simplest version of CPA doesn't have any vertex corrections at all. And I'm trying to get a feeling, what are these vertex corrections? What is their physical content? Because I know that from literature that there are such vertex corrections which bring some angular dependence to the scattering rate, but they don't give you weak localization. These ladders, these diffusons, but then there are also maximal cross diagrams. So they are actually vertex corrections that have different physical content, and none of them are contained in a single in the simplest CPA approximation. So I would like to understand, what exactly is this particular version or approximation scheme? How is it related to the standard CPA?
The point, show the formula again for the conductivity.
Yeah.
Yeah. So basically, if you we can probably see it already. Well, see it already in 8 that basically you have the problem in disordered systems theory. We'll just go, maybe it's one further back even than that. I can go just a second. Yeah. This is fine. What you've got to do is you've got to average the product of 2 Green's functions, right? And the simplest thing to do is just to say the product of the 2 Green's functions is just the square of one of them.
Exactly. That's exactly
and
what
these
those
vertex corrections here are the stuff that takes care of the fact that it really is the product of 2 Green's functions, and you have to preserve whatever theory you have to preserve that relationship. And it's not entirely trivial, and it was a bit of a mystery to begin with when Bill started to work on this conductivity, exactly how you average the product of 2 Green's functions to be consistent with the KKR-CPA, so that you don't get non-analytic behavior and all this kind of stuff. We'd already solved the problem of how you average a single Green's function.
Well, no, I know that, Marco. What I'm asking is that, in what became kind of clear when the DMFT came about is that if you go to the limit of a large coordination number, and then the self-energy of the average Green's function becomes purely local
that's true.
Then there are vertex expressions, but they drop out of the Kubo formula. The ones that they refer to, like in the Mahan's book, there are these ladder diagrams. They drop out. So the CPA expression for the single band model, that expression has only a product of 2 Green's function. The average Green's function doesn't have any vertex corrections. Now, I understand that if you have a more complicated situation with more bands, or the situation may be complicated. And in general, the exact expression, not in a CPA approximation, but an exact expression, of course, it has these vertex corrections, but I'm trying to get the feeling of what, how is this related to a simple CPA and not to this KKR-CPA?
Well, it's true in the simple, the statement is true for the simple CPA.
But it doesn't have vertex corrections.
Well, I mean, I can write a one-dimensional model. Bill Butler did that a long time ago. Just you can write the say in one dimension. You can take a set of disordered array of potentials, A and B potentials, just plus and minus something, for example, and you can cast that into multiple scattering language with no problem. It's the same problem. I mean, multiple scattering theory provides you with, again, an exact method of solving the equations, right? I mean, of solving the Schrodinger equation.
That's not my question. My question is, there's a CPA, standard CPA approximation defined by whatever diagrams they remain non-zero in the limit of large coordination. So it's you can say it another way. You can sum all the diagrams that are local. They give you local self-energy. So that approximation is a conservative approximation in the sense of Baron-Kadanoff. And within that approximation, like in general DMFT theory, there are no vertex corrections at all. Right? Now, so I'm trying to get a feeling, when do we need to put these vertex corrections and when do we don't? Because normally in the DMFT type of approaches, which I think includes KKR-CPA, there are no vertex corrections.
I think I can probably. So I think you're asking for which systems vertex corrections, conductivity vertex corrections are important, and for which systems they're not.
Yeah.
Okay. So I think so. If we go a few slides later, so if you look at silver palladium, you can see that at low silver concentration, so the red plot is without vertex reactions, the black one is with vertex reactions. Now at this end here, I think there's majorly D character for the bands at the Fermi energy, and at this point vertex reactions are not that important. But if you look at copper zinc, so you can see that vertex reactions are significantly important, because I think whenever you have multiple orbitals
Right.
character at the Fermi energy, there will be some backscattering.
But
And
is this a single site KKR-CPA still or not?
yeah.
Or
It's
it
still
is
single
not a
site
cluster.
KKR-CPA.
It's not a cluster. Because it's clear that once you go beyond a single site, you go to cluster, there are always vertex fractions, right? Which you cannot drop. But in the single site case, my understanding was that, and maybe other people here who are more who has been working really on CPA and on TMT before, then they can comment on that. My impression was that in the single site case, you don't actually have to put a because they would cancel out, at least in the single band case.
If you are calculating some quantity that depends on a single Green's function, it's just the imaginary part of the trace of some Green's function and maybe some operator that operates on it. It doesn't matter. So it's just that the question is how do you calculate observables?
Yeah.
And so to the extent that, say, the density of states or band structure is an observable, those are derived from the Green's function, period.
Yeah.
The conductivity, and the Kubo-Greenwood formula tells you this, the conductivity, it depends on the product of two Green's functions.
Well, yeah.
So when you decouple those two Green's functions, you have to do it in a way that preserves unitarity, all of the conditions that are required on the Green's function.
I know. This is why I'm asking this question. That Kurana proved that when you have a local Green self-energy, then the vertex corrections cancel out within the Kubo formula. That's been proven in the approximation where you have a purely local self-energy, at least for a single band model. So I'm not saying that they don't exist. I'm just saying that in a particular approximation, which becomes exact in certain limits, then these vertex corrections can be dropped out. And normally people say, well, the non-local terms to the self-energy, they can be captured by cluster corrections. And then of course you have to put vertex corrections. Those are never zero in finite dimensions. They are finite numbers. But some vertex corrections, like the maximum closed diagrams, they actually blow up in low dimensions, and others don't. So they're not equally harmless.
In a sense, you are in the Kubo-Greenwood in the Kubo-Greenwood formula. You are saying that I've got there's a correlation of it's just the scattering difference in scattering in and scattering out terms. So if the Fermi energy, it turns out in general, if the Fermi energy sits in the D bands, which tend to be where the self energy becomes big and the bands become very smeared out, the vertex corrections, these vertex corrections that we're talking about here, don't matter. It's when the Fermi energy falls in the SP bands,
okay,
where those vertex corrections are a substantial fraction of the overall scattering. So.
Okay, or maybe we can return to that later. Let me know if you got the talk further.
So this is basically the expression that you have for conductivity, and you have this. The most computationally intensive part of this calculation is calculating this chi matrix, which is you're calculating the Brillouin integral of the two tau matrix product, and generally this can be simplified by just integrating over the irreducible Brillouin. and using the symmetry properties of your crystal to then multiply with the rotation matrices to recover the other parts of your integral, which is what we're also doing. So here's some systems on which we have applied.
Can I ask a question about that in this codes, the coding that you've been doing?
Yeah.
Is this true for all the crystal structures that are your codes limited to sort of FCC, BCC, or can you do HCP and rhombohedral or whatever? So all of this group theory that you're using to do this integral, is that general? So it doesn't, provided I tell it what the crystal structure is, it will do that integral for me.
Yeah, it should okay. Because in the formulation we're just multiplying this tau by u times u dagger, which is the rotation operator. So there's nothing specific about the crystal about this.
I'm going to say, so if I say that the system is when we initially did all this stuff, it was pretty much confined to FCC and BCC, and but I think in the Munich code, it's fairly general. And I was wondering how, in terms of crystal structure, how general your codes are.
I think it should work because we haven't used anything about cubic. The only approximations that we used is for the muffin tin. Mm-hmm. So we've employed that we are using muffin tin potentials, but apart from that, it should work for anything.
This code basically, you tell the crystal structure, it generates the rotation matrix for you. It's not constrained to the
So just like it does for the tau matrix itself, right?
Yeah. Actually, that part of code I got from you. I don't know where you get it from. It's a general.
You get to a certain age. You get to a certain age, young, that you don't even remember what it is you did.
Okay. I don't know where the code come from. Okay, I know it's come from you.
Yeah.
I guess you get it from somebody else.
Yes, I probably stole it from someone else. Yes.
Yeah. Okay. Good.
I
hope we don't have the illegal problem.
No, I don't think so.
Also, I think maybe for the vertex extractions, it should also be helpful. So you have this omega matrix here, which is this average of these two X matrices in CPA. So we can mathematically see it as the average. So if you express this as this average product, if you approximate it as the product of the averages, then the average X matrix in single site CPA goes to 0, which is how you get your iteration, this is the iteration scheme, which is how you get the CPA medium. So when you set this to 0, that is equivalent to not ignoring vertex corrections. So mathematically, we can also see vertex corrections that way. So if we go back to copper zinc, so the left-hand side plot is obtained using the Munich code. They have a bunch of different plots because they also have some short-range order. But what we need to compare is this black dashed plot with the black plot on the right, and these red crosses with the red squares on the right, because that's the single site result of without and with vertex corrections. So you can see that for this system, there's quite a significant effect of the vertex sections due to both S and D character at the Fermi energy. And so vertex sections need to be included in this system. There's also the slight anomalous region of resistivity that we found near 0.1, which you can see has not been studied in the Munich one. They've sort of skipped over that point. And we also couldn't find any experimental data because most experimental data is for copper rich region, because you can mix more zinc in copper than you can copper in zinc. So
do you have a physical interpretation of that boundary? Is this some sort of multiple scattering process, or what do you think it is?
We're not really sure because we looked at the density of states at this point to see if there was something different there, but we didn't see anything in the density of states. And also there's no physical, because we're studying a BCC crystal at all copper concentrations, but at this concentration, copper zinc is not BCC, it's something else. So
let me ask my question in a slightly different way. If you actually went to a model or a material that actually would have some sort of bound state forming the entire band, like the adversarial causation, right? Then the question is, what would, here we are showing the vertex correction, adding the vertex correction gives you a factor of 2 difference. Okay. Now, we know that with CPA doesn't capture localization, and the resistivity will remain finite for any finite amount of disorder. But the question is, what will happen to these vertex corrections? Would they solve that problem or not solve the problem, or what would, the point is that, this is kind of anecdotal evidence. Oh yeah, I applied to one particular example and I see a difference, but the regime where disorder effects, which are beyond CPA, are very, very strong, in particular these vertex corrections, is when you have localization. So do you know of people trying to apply the same exact approximation, same formulation in a regime with localization? Do you have any recollection of something like that?
I'm not sure. So, I mean, the silver palladium example does not, so the vertex sections do not have a significant impact there.
The thing is that, these are all good metals, and good metals we can have what they call weak localization, but we don't have really a real bound state forming. So it's, the question is, when you add some corrections and some additional improvements of your theory, is this a quantitative issue or is it a qualitative issue where you can be missing something really dramatic? That's what I'm trying to get at.
Yeah, the vertex sections represent something physical, if that's what you're asking.
It's physical, but the question is this changing the result by a factor of 2, or you can be changing in some cases the result by a factor of 10,000? That's the question.
No, that is no. I don't think that is.
Definitely. What they found in the scale interior localization, they put these maximum cross diagrams in 2 dimensions or in 1 dimension, and then the conductivity doesn't go to down by a factor of 2. It goes down to 0. Right. So then basically ignoring enough dimensions, some of the vertex corrections they blow up. And because they blow up, then the result is totally different than, but that's not always true for all vertex corrections. And that's why it was kind of, I think one shouldn't be missing, corrections that are quantitative from corrections that are qualitatively huge in some cases, right? Maybe the answer to that question is not obvious, and that's okay, but I'm just trying to get a feel.
Yeah, I mean, generally, we believe that whenever there is high smearing, extremely high disorder, and we expect that the Fermi surface is highly smeared out, that the vertex sections won't have that much of an impact. And otherwise,
so this is opposite from what I'm saying, because when the disorder is very strong, then that's what Anderson showed in 1958, that if you take a single band model and you put disorder which is sufficiently strong, then the entire band will localize them from bound states. And so in the limit of strong disorder, and now that will not happen if you ignore vertex corrections at all, right? So that's what the point was, why CPA was a trouble child, in the sense that it will not give you this Anderson transition. And the culprit is the vertex corrections, precisely, right? Because if you average the Green's function doesn't show any phase transition at the Anderson transition. It doesn't show anything. It remains, the density of states remains finite, whereas the conductivity drops to 0, right? And so it is the vertex corrections that are producing this effect. Certain vertex corrections are producing this effect, but there are types of vertex corrections that don't. So, I think it's difficult to say, oh, vertex corrections always do this or always do that. That's my point, I know we come from a slightly different communities where people are interested in slightly different questions. And maybe in this case of metallic alloys, this is not particularly important what I'm asking.
Yeah, just a comment to put this in perspective. The the systems that we've used, these methods have been used to used for you know, are metals.
Yeah.
So, and typically the resistivity in these alloys, let's just stick to single phase alloys so that we don't have any ambiguity, goes from basically 0 to typically maybe 100 and odd, 150 or possibly a slightly more micro-ohm centimeters. Which is so we've looked at systems where you approach this what's it called, Mott-Ragel limit, right. And basically in KKR-CPA what it does for you is it shows you as the resistivity gets very, very, very large. The reason for this is that the what you will call the bands, i.e. the spectral function, is very broadened.
Right.
So if the
density of state
the half width of the band is basically the Brillouin zone dimension, which means that the mean free path is the order of 1 atom wide, right? So you're already in the bordering on the localized limit, right? So this is the regime where you're operating, as Vishnu said, the things like copper, zinc, and silver palladium. When you get mostly silver, the Fermi energy is in the sp bands, and that makes about a factor of 2 or so difference in the resistivity, whether you put in the vertex corrections or not. And that's one of the clearest cases where you can see the effect of these vertex corrections that he's putting in here.
Right, and they actually make the resistivity drop.
Yes, yes.
Which is
our first calculations on silver palladium, way back. I don't know whether the terms were used, but I think we even said that this was the lack of that we didn't have the vertex corrections in to begin with.
Yeah.
And so we then did the thing that thing that physicists always do when they don't understand it. They don't get the right answer. They invoke some other effect, right? And so we said we blamed it on vertex corrections, right? Which then, when they were put in, actually did show that it was correct. But
right. Well, all I'm saying is that, you know, if you always ignore vertex corrections, then you will never get undersoil causation, which means that the resistivity is over or underestimated. So these vertex corrections that I was talking about, they actually make the resistivity go up, and it can make them blow up in all dimensions and so strongly disordered. Whereas these vertex corrections you are talking about are completely different in their physical character. They describe some physical processes that are so completely opposite from what I was talking about. So this makes the resistivity lower, or the system is more metallic than, so these are not kind of vertex corrections that bring in undersoil causation effects or precursors, but in fact the opposite, right? That's what I was trying to get to, to get a feeling what is the physical content of that, and not just the technical. The formulas are very complicated, and I get confused, because I'm unfamiliar with this is very complicated and very sophisticated, and much more than in a single band model. And people like me who come from a simple background, it's overwhelming, and I'm trying to get a feeling what is the content of that. But I think now we are getting basically that this is a kind of effect which is opposite for undersoil causation effect, right? That you are discussing.
Yeah, I think probably the confusion is that the vertex corrections that we're talking about is only associated with conductivity and has nothing to do with the effective medium. Our effective medium is still single side, but I think the vertex corrections that you're talking about is about the including correlations in the effective medium itself?
No. I mean, if you do weak disorder in all dimensions, but perturbative means, this is what the Gango-4 and the scaling theory did. Then they assume that the single particle Green's function, the average single particle Green's function, in other words, the density of states, doesn't do anything. It remains finite at the Anderson transition. So what you call medium, effective medium in CPA, is basically the density of states, right? The density of states is not a critical property of the Anderson transition. And so they are not concerned about any corrections that change, the density of states by a finite amount, because that's not a part of this phase transition again. Whereas when the conductivity drops to 0 and there is a phase transition, that is not affecting the average density of states, but it's affecting only the conductivity. And so what they show is that there is a subclass of vertex corrections which do the task, right? The Green's function doesn't do it, the effective medium doesn't do it, it is the vertex correction. So it's not cluster CPA that does that. In fact, that's the reason why Gerald, when Anya went to work as a postdoc for him, he was working on cluster versions of CPA, but he became aware of the fact that unless you go to infinite cluster, that's never going to capture Anderson causation. And then they try to do something different, right? So it's not a medium. I mean, there are correlations in the medium, they do change numbers, but that's different from the physics of Anderson causation. That's all I'm trying to say.
Can I just ask you that picture? On your calculations on the right. So on the right is pure copper, right?
Yeah.
And on the left is a kind of weird zinc because it's and so this sort of dip here. You say you can't figure where that comes from. I mean, the thing that you're doing is you're putting more electrons in, right, into the band. And another electron. So there must be some feature in the block spectral function, the Fermi energy, that gives rise to this funny behavior. And it'd be kind of interesting if you could look at this block spectral function, just pick a few directions, the typical directions for the FCC Brillouin zone, 0, 0, 1, 0, 1, 1, etc. Those, and have a look to see where the Fermi energy is falling on that block spectral function to figure out might be able to figure out what's giving rise to this peculiar behavior. But this is the first time I've seen this, and so I'm kind of curious.
Yeah, we should. Yeah, we haven't looked at the spectral functions yet. Yeah, we need to do that. Yeah.
It would be nice.
Yeah. So
but again, for this, trying to look at it with the same scale as the previous calculation. I know that there are basically no points that they had calculated in this region, but to the right of basically point 2, I'm trying to figure out how well years and the Minicode calculations agree.
yeah, I think they're kind of close.
Yes.
Probably
What would be
0.5 to 1 micron centimeter, maybe maximum difference.
I was trying to do sort of the comparison, but it would be nice sort of to see them on the same scale, on the same plot or so.
Yeah. I think the scale is probably
because they are. Oh, I mean, your axes are labeled the same. I mean, they go both from 0 to 20 and from 0 to 1, but because they have different aspect ratios and sizes, it's very hard to compare.
Yeah, I mean,
it looks like it's happening right where the calculations on the left
Stop, yeah.
they stopped doing it. Maybe they saw that bump and thought, I have no idea what's causing that, and quit. You know what I mean?
I mean, it's quite suspicious that they did this sort of, what is it, 0.18 or so. And,
yeah, exactly. They maybe thought that this can't be right, and we'll just stop calculating here. And that's why I thought it would be good to go in and look at carefully to see if there are any obvious structures in the density of states, but more importantly, what does the density of states at the Fermi energy? But most importantly, what do the bands, the block spectral function look like? What's the broadening look like? All that kind of stuff. The broadening still has to be small because the resistivity is only, in the end, it's only 5 microohm centimeters, which is small, right? It's a very small resistivity. So,
yeah, so
it may be hard to pin it down, but it would be, I think, interesting because there must, you know, there's always a pretty good reason in terms of the underlying band structure of why something behaves in this kind of way. So.
Yeah, we need to look at the block functions. We've looked at the density of states, and we haven't really.
You don't see anything. Yeah, I think that quantity is an integral over the zone. It may be that in some direction, some band is going into the, you know, it may be just some structure in the density of states that's at the Brillouin zone boundary or Brillouin zone center, or some band that's turning over or doing something, you know, splits or something. I don't know, but it would be interesting to know.
So the second case we looked at was silver palladium, which is again very well studied. The left plot is from the same paper that was before, and the blue one here is the experimental plot. So what you need to compare is the pink one with our red one, which is the one without vertex extractions, and the green with the black one, which has vertex extractions included. So as it was mentioned, when you have palladium rich, your Fermi energy has mainly just D character, and you don't really see the effect of vertex extractions. Whereas as you go towards silver rich regions, you have more S character, and you can see that there's quite an impact, a significant impact of including the vertex extractions.
But the reason why, there's a separate question not related to that. Why is this resistivity displaying such a sharp peak at around 0.4? I mean, you would think that naively it should be something like a parabola, right? Maximum at the 50% and smooth with concentration. Why is there seems to be a very sharp peak at one particular point? It's almost like two linear behaviors are intersecting. Is there a simple reason for that? There's got to be some reason.
I'm not sure if this is the correct reason, but I think the transition from D to S, when you're going from silver rich to palladium rich, the difference in the chemical behavior of the two is quite different. So maybe that's why you see a different conductivity behavior at the silver rich region. Could
it be that the Fermi surface is somehow shifting from one band to another band, or you know, as you drop? The point is that, you know, you can give various arguments, but all naive arguments would give you smooth behavior with concentration and not such a sharp peak. So the sharp peak is kind of a big surprise. You know, I would not have guessed that, right? Why would there be this? It almost seems like a phase transition, but it's not a phase transition, right?
No, this is all at FCC.
Right. So why? What is happening here? It's if someone comes in and says what's going, and we can see it also in the experiment. That basically below 0.3, it's completely linear with concentration, and at high concentration, it's again almost linear, and it almost seems like two straight lines intersecting. It's really striking that this is so different than the normal guess, which would be a problem.
Yeah, I think it's probably due to the orbital character of silver and palladium.
Yeah.
The two extremes, probably as opposed to copper zinc. But I'm not fully sure if that's the exact reason.
They're like really sharp though. Can you like maybe take more data points and see if it's a little bit more rounded about that peak or?
Yeah, but I think it is probably sharp at that point.
Okay.
Yeah. So the next set of systems that we tried was to recreate the conductivity of Cantervue alloys, which was actually studied in the 2018 paper by Saimu. So basically, the interesting thing here is that you have sort of the alloys fall into two categories. So your Cantervue alloys are alloys which contain cobalt, iron, nickel, manganese, chromium, and in this case, we also have palladium. So you can see that you have this first category here, which has very low resistivity, and then you have the second category here that has very high resistivity, with almost 2 orders of magnitude high.
Wow.
And that is mainly because if you put chromium or manganese, this antiferromagnetic elements in these alloys, your Fermi surface ends up getting quite washed out, and the mean free path becomes very small, and you have high resistivity. Whereas if you don't include any of those antiferromagnetic, and you have mainly ferromagnetic elements along one spin channel, your Fermi surface is very sharp, and you have large mean free path, and you see a lesser resistivity, much smaller resistivity in these systems.
And can you comment in your calculations? Are you taking into account magnetic order in any specific way or not?
We're doing a spin polarized calculation.
So does that mean that in some cases it actually becomes antiferromagnetic, or spin polarized usually means all everything is polarized in one direction, or what do you mean by spin polarized?
So we are that means we are including, so each element species can be spin up or spin down in your single side. So generally in these calculations, we notice that chromium and manganese have a negative spin, and your cobalt iron have positive.
I see. So you're getting magnetic order here. You're capturing magnetic order.
Yeah.
And if you didn't put magnetic order, then the results will be very different, right?
Yeah, if we don't include spin, then yes, you would expect.
I see. So you're saying that this large effect is because of the magnetic order is creating, once you put magnetic order, then this magnetic order will create a large random potential when you randomly mixed elements, because each element is differently magnetized, right? And so this is that's the reason for the strong disorder, right? The magnetic order is creating this strong disorder.
Yeah, because generally when you put elements that can have, some of them are strongly spin up and spin down, then you see that effect. But in these first four elements, all of these elements are mostly spin up, and you see a very high conductivity along one spin channel.
But usually the magnetism is temperature dependent. And how does the experiment, how is the resistivity responding to the changes of magnetism? Or some of them may not actually be magnetically ordered like that.
Yeah, I think these calculations are all at 0 Kelvin. So
right, but is it known what is the temperature dependency from experiments, or?
I mean, normally you would expect the Curie temperature, it should show some magnetic order. I'm not sure what the Curie temperature for these alloys are.
So my question here also would be, does the CPA calculation is actually capable to capture the magnetic order, especially in the systems with where you have antiferromagnetic coupling correctly. I mean, you would expect if you have now randomly placed ferromagnetic and especially antiferromagnetic coupling that have quite a lot of frustrated interactions.
Yeah, this is something that Sai and we studied in great detail, and there are further papers about some of these things. But what's already been said is that iron and cobalt are both ferromagnetic, and so in a random alloy, they're perfect. Just a second. Barbara, can you stop spraying the thing? I can't hear. It's on me, it's making all the noise. Sorry, we're expecting, so when you make an alloy, the iron and cobalt tend to align nicely. But when you add manganese or chromium, they themselves want to be antiferromagnetic, so they don't know whether they want to align or misalign with the other elements. Basically what happens is, for the most part, the moment on chromium does go, chromium and manganese does go antiferromagnetic with respect to the other elements, iron and cobalt. But again, with the chromium moments much quenched. And that's, if you do supercell calculations, you also see that. What's the one that's interesting is manganese, because manganese, it will want to be antiferromagnetic to nickel and cobalt and iron. And so that's what you see in the KKR-CPA. If you do a supercell calculation, what you find is some of the manganese elements are up and some of them are down relative to cobalt. Right. But it turns out, actually, what you can do is you can say, in the KKR-CPA, you can say, aha, I don't like this. Can I find another solution? And one other solution is that half the manganese point up and half of them point down, right? And that's just like an extra component.
Right, which is
and
like
then you do that, and what you find is that you do find, in fact, a magnetic ground state with half the manganese up and half the manganese down.
Right.
And that state corresponds pretty closely to what you see in the supercell calculation, because again, it's about half of them are up and half of them are down.
So this is the same as doing some mean field theory of spin glass ordering. That's basically what you do in the mean field theory for spin glass ordering. So basically, more formally speaking, if you want to capture magnetic order within single site theories, you can do what they call EDMFT. Or in other words, the cavity can acquire magnetic moment, but in random systems, this the internal field from a cavity can also be randomly distributed, and that can be done self-consistently, like Malcolm is describing, and capturing this within a single site type of theory. So I think, yes, I now I'm starting to understand how, in fact, you can capture spin glass ordering within single site theory if you properly formulate, right? And that's what you've done, right?
Yeah. Okay, so now we thought we'd apply it to some high entropy alloys. Specifically, we want to apply it to this aluminum, cobalt, chromium, iron, nickel, where we vary the amount of aluminum. And this is an interesting system because we took this experimental data where they had sort of used this vacuum arc remelting, and they had homogenized it, basically kept it at 1100 Celsius for a day, and then they quenched it. And this is what they call their as homogenized samples. And experimentally, they found that for aluminum concentration less than 37.5%, it's a single phase FCC. And above the equiatomic case, it's BCC. Although for some cases they found B2 plus BCC, but we're not really taking that into consideration because we're doing single site. But in the intermediate regions between 37.5 and the equiatomic case, they find sort of multiphase FCC plus BCC, with the FCC phase sort of slowly going to zero and the BCC phase increasing. So we wanted to study from first principles what the resistivity would look like for this system. So we did two examples. So I should again go back. So over here, you can see a sort of interesting thing here is that even though it is designed at, the aluminum is designed to be at a certain concentration for any of these samples, you can see that the actual experimental concentrations for the FCC and BCC are different. So you find that the aluminum, especially say if you look at the 50% one or 75, the aluminum prefers to be in the BCC phase as opposed to the FCC. You can see that the FCC aluminum is pretty much stays constant at about say 7 near 8%. So basically we did two examples of this. The one on the right is where we use the nominal concentrations for the different elements, basically the concentration that you would theoretically expect. And on the left, we use the experimental FCC and BCC concentrations for the different systems. So you can see that when you use the nominal concentrations, you get the standard monotonic increase as you add more aluminum. There's a shift between the resistivity of FCC and BCC, but you can see that it's mostly monotonic. And if you take some sort of a naive series and parallel average between the two of them, you can see a fairly constant increase, which doesn't really match with the experimental trend here, which is a sort of non-monotonic decrease. But if you take the experimental concentrations for the FCC and BCC, since the aluminum concentration remains pretty much constant in the FCC phase, even when you add more aluminum to the system, you can see that the resistivity of the FCC phase doesn't change that much. It's slight decrease, but it mostly nearly stays constant. But the BCC phase seems to almost mirror the kind of behavior you see in the experiment, and that sort of matches the non-monotonic behavior you get. So essentially, this shows like sort of the significant effect. The non-monotonicity of the resistivity in the multiphase region essentially arises from the fact that you have different concentrations in the FCC and the BCC of the aluminum. The aluminum doesn't equally go to the FCC and BCC. And there are some other points here in that we expect that the first principles calculation will be smaller than the experiment for two reasons. One, we are taking sort of simple crystals which don't have any defects, but the actual microstructures present in the sample will have some defects, which will have more increase the amount of scattering. And also this curve is at room temperature, and ours is at 0 Kelvin. So we should expect some gap due to that. So we also wanted to analyze why this is happening. And you can see, so the non-monotonicity is due to the multiphase behavior, but there's also this increase in the resistivity. So you can see that overall, as you add more aluminum, your resistivity is increasing. So we took a look at the density of states. So on the left, you have the sort of concentration average density of states. For the black one is with 0 aluminum, and the red one is the aluminum to cobalt chromium iron nickel. And the one on the right is the partial density of states for the aluminum 2 system. So you can expect that the density of states will be smaller at the Fermi energy for the system with aluminum because aluminum doesn't have any d electrons, and that is what we see. However, the density of states at the Fermi energy alone is not a real indicator of whether you would have higher or lower resistivity. And for that, better reasoning can be obtained by looking at the sort of iron, cobalt, and nickel, which are the sort of late d elements. And what is actually been studied and what happens is that there's a SPD hybridization. So basically, these elements take electrons from the S&P of aluminum and fill the d orbitals. And the S&P conduction electrons are hence taken up by these elements. So as a result, you see lesser conductivity and an increased resistivity. So that is the reasoning that we believe is resulting in higher resistivity in the aluminum, cobalt, chromium, iron, nickel. And the reason we don't directly infer this from the density of states. So what we initially thought by just looking at the density of states was that since this system has lower density of states at the Fermi energy, it should have high resistivity, but that is not true. That is not guaranteed, as we can see from the next system. So for the next system, we studied this refractory high entropy alloy, which is molybdenum, niobium, tantalum, vanadium, and tungsten. But as a concentration of as you increase vanadium concentration. So in this case, again, we observe a sort of, this is a single phase BCC, so there's no multi-phase behavior here. And we're seeing an increase in the resistivity as you increase vanadium. So to study that, once again, we calculate the density of states. But in this case, we observed something reverse. So as you add vanadium to the system, we saw a higher density of states. So even if you look at the partial density of states, vanadium has a higher density of states at the Fermi energy as opposed to the other elements. And you see an increase in the density of states as opposed to the decrease that we saw in the aluminum case. Now, to reconcile that, we can look at the sort of sizes of the different elements. So vanadium is smaller than some of the other refractory metals. So this adding a smaller element compared to the other elements will increase the disorder in your system. And we expect that this should have increased scattering. And also, since this is smaller, you would expect that if you allow it to fully relax, like you would do for a supercell case, then some of the bonds with vanadium, say a tantalum vanadium bond, you would expect that to be shorter than a tantalum niobium bond. But since we're doing CPA, we don't really allow that to happen. You have all your bonds to be a similar size. Then your actual tantalum vanadium bonds are bigger than what it would like to be. And since they're more far apart, the density of states you can expect should be more atomic-like. Because if you put two things closer, then you'd see stronger bonding. You should see a flatter density of states. And if they're farther apart than you want them to be, then you will expect more atomic-like behavior. And
but Vishnu, I heard that in maximum entropy alloys, the local bond length surrounding a given element is not actually as random as you may think. That actually, if you randomly mix them, then the crystal is surprisingly periodic. And so, the fact that the elemental elements have different lattice constants doesn't necessarily mean that if you have an alloy and then surrounding niobium, you have a bigger lattice constant than in the region where there is more tungsten or something like that. Right? So that's a non-trivial issue, right? That the alloy may adjust the bond lengths to be more uniform in some cases. Is that and there's experimental data on that. So what's the case here?
So in this case, I mean, we didn't really see any experimental data for this. So we're not sure experimentally what happens, but we would expect that since vanadium is, say, almost 10% smaller lattice constant than, say, niobium or tantalum, we would expect that the bond lengths would be slightly shorter in that case. And that would also make sense from a density of states point of view. So you can see that the density of states for vanadium is, the width is smaller and it's more peaked as opposed to some of the other elements.
Yeah.
And you can explain that by, if there are weaker bonds due to them not being close enough, then you would expect that the density of states should be more peaked. So that seems to sort of make sense with that picture.
Yeah, I think the average bond length will change, obviously, with the mixed elements. But the question is, how is the variance in the bond length affected? And I've been told that in many alloys, maximum entropy alloys, the bond lengths are remarkably uniform throughout the crystal, even though you have random concentrations of different elements. So it's that's kind of, I've been told that this is one of the mysteries, or anyway.
Yeah, I guess we would have to do some sort of supercell calculations.
Yeah. We like seeing it.
Yeah. So that is basically how. That is basically why we believe that even though the density of states is larger, and naively we would expect that the density of states at the Fermi energy sort of indicates the conductivity, and the higher density of states might lead us initially to believe that there's higher conductivity, but that is not the case. The larger density of states in this case is attributed to weaker bonding. So that is sort of the summary of my talk, which is that we implemented this technique in our code, and we sort of initially applied it to some systems that have been studied previously, except for the copper zinc, where we found a slightly anomalous behavior at 0.1 copper concentration that we haven't studied yet. And we applied it to the multi-phase high entropy alloy, and we managed to recreate the experimental trend that was observed in the non-monotonic region. And we sort of attributed this to the fact that some of the transition metals take up some of the aluminum S and P electrons, and you have a lower conductivity. And we also sort of gave a prediction for this refractory high entropy alloy as a concentration as very vanadium concentration. And in this case, even though the density of states was higher, we believe that is due to the size difference of vanadium. We predict that there's weaker bonding there, and that results in a more peaked density of states. So yeah, that is my talk. If you have any questions.
It's a very nice talk. So we also had a lot of discussions. So it's taking almost an hour and a half. So anyway, any other questions?
Hi Vishnu, very nice talk. So I had a quick question. So in your calculations, do you do spin polarized or spin unpolarized?
Spin polarized. All the calculations are spin polarized.
Okay. So yeah, sorry, go ahead.
No, just that in this the molybdenum niobium case, there's no spin. We have done a spin polarized calculation, but it's not.
Okay. And also, I'm guessing that you did your calculations on bridges, right? Like
no, we did our calculations on our local
okay,
group
CMU cluster. Okay.
Yeah.
So how long does one of your calculations take?
It really depends on the K point. So I did it at for these. I use sort of a high K point grid, 70 cross 70 cross 70. So that probably takes about, on 40 cores, I think 2 hours to 2.5 hours.
Okay.
Yeah, I think with the symmetrization of the Brillouin zone, the calculations don't really take much time. Okay. For CPA,
so that's 2 hours for each concentration for the conductivity calculation.
Yeah, each concentration. Yeah.
Each concentration, 2 hours.
Each single calculation.
Okay.
So, thank you. Was really very interesting.
Yeah, very nice.
So the last thing I wanted to bring up before we close is actually the hackathon in October. Yeah, so ORNL will have a hackathon for OpenMP porting codes to GPUs. And I was proposing that we submit a team for that. And we would, we need to know who, and the idea would be to target the MST code, I think, for acceleration using GPUs.